Hello everyone. In the last class, we have learned up to missing data management in the MATLAB. Today, in this lecture, we are going to learn about data smoothing and outlier detection. Okay, so data smoothing refers to the technique for eliminating unwanted noise or behaviors in data. So there will be unwanted noise, unwanted, that is unimportant data present. So how to remove that data? So unwanted data is termed as a noise. So how to remove that noise or unwanted behaviors in data? And also, while outlier detection identifies data points that are significantly different from the rest of the data. So first, so the very important and very prominent method is moving window methods. So in the moving window methods are the ways to process data in smaller batches at a time, typically in order to statistically represent a neighborhood of points in the data. So you have a very big data. So what you do is you convert that big data into a small batches of data. On that particular batches of data, you will move the window, and whatever the points comes inside the boundary of the window, those represents the neighborhood of the data. Neighborhood means next points of the data. For example, 2 3 4 5 6. So 2 3 4, after that the neighborhood is not 6, the neighborhood is the 5. Like that we can find it out. The moving average is a common data smoothing technique that slides a window along the data, computing the mean of the points inside of each window. So whatever the points comes inside each window, it will calculate the average. Average is nothing but our mean. Okay, mean is a internal function of the MATLAB. This can help to eliminate insignificant variations from one data point to the next data point. For example, we have taken one example, that is, consider a wind speed measurement. So we wanted to measure the speed of the wind. Okay, that was taken for 3 hours. In the 3 hours, we have recorded the speed of the wind for every minute. So now, in to measure the speed of the window, what we are doing is we are using the move mean function. There is a function, inbuilt function in the MATLAB, that is a move mean. So use the move mean function with a window size of 5 minutes. So what is the window size? That is a 5 minutes to smooth out high speed wind gusts. So now, to understand how to compute this move mean function, I have written one program, that is data smoothing.m. So now we will go into the program and we will see what is present, how we are calculating that. So let us go to the MATLAB. So this is a MATLAB window. So inside that you have data smoothing.m. Okay, data smoothing.m. So I have opened the data smoothing.m. Now I have a recorded data, that is a wind speed for every minute, that is the wind data dot mat. The dot mat means matrix form of a data. So now first command indicates we have to load this data. Okay, then we have to see the minutes. So for every minute, what is the length of the wind? So how we are doing that? So in this window data dot mat, there is a variable called speed. So we have taken the speed and we are computing the length of the speed by using the internal function, that is the length. Now we have taken the window size is equal to 5. Now we wanted to calculate the we wanted to do the average, that is by using the move mean function. We are calculating mean speed is equal to move mean of speed comma window, and for that whatever we have calculated, we are now plotting the graph, that is a plot minutes comma speed and again minutes comma mean speed. So our x-axis is we are taking x-axis in minutes, and on we have two y-axis. One is the speed, another one is the mean speed. And here axis type means perfect x-axis, and for that we have used the legend. So one legend is measure the wind speed, second is average wind speed over 5 minutes of window, and we are labeling the x-axis as a time and y-axis as a speed. So now what I do is I will copy each and every command from this to understand for you, and I will run that. So you can see now so you can see here, this is the variable that is present inside the uh, data dot mat. You have the variables, so in that one of the variable is speed, we want this one. Okay, now minutes is equal to 1 to length of speed of the window. So this is the minutes. So minutes we have taken, that is 1 by 186. You can see here 1 by, this is 1 by 186, that is 186 columns, and the data type by default it is double data. Okay, and now window size I have taken as 5. Window size I have taken as a 5. Now mean speed, I'm calculating mean speed. Mean speed is equal to move mean, that is I'm taking the average by using the function move mean, and I have computed the mean speed, so that this is my mean speed. Okay, this is my mean speed. This is 186 by 1. So these are the values of the mean speed. Now I am plotting the graph. Okay, so this is the graph. So for that what I am doing is, now I am adding even the legends. So this legend, that is measure wind speed, two legends, measure wind speed and average wind speed over 5 minutes of window, and I'm labeling now x-axis as a time and y-axis as a speed. Okay, now you can see the graph. Now you can see the graph. Yes, I'll maximize. Okay, you see this graph now. This is a y-axis, that is speed, and x-axis is a time, and here we have legends here, that is two. One is a measured wind speed, this is measured wind speed, and this is the average wind speed over 5 minutes of window. The colors you can indicate. So this is the wind speed over 180 minutes. I have taken up to 180 minutes. Time is in minutes. Okay, similarly you can also compute the median wind speed over a sliding window using the move median function. Okay, so let us go again to the same program. Yes, so here that is a median speed is equal to move median speed of the window. So I am calculating the median speed. Okay, again I am plotting with median speed. Plot the graph. Now axis tight. Now legend. Now x label time, and again y label speed. Okay, now you can see the graph. Yeah, you can see this is the, see, this is the measure wind speed over 5 median. So this is the median wind speed. You can see this color, you can see this, you can see this. Just I'm zooming. So this is the median. I have calculated median. Again, this time I have taken up to 65 seconds. 65, this is seconds, 65 seconds I have taken. So okay, that is the zoomed. I have taken zoom up to 65, and this is complete time axis is 180. Okay, now so here we have, till now we have seen the two methods, that is, one is the mean and another one is the median. But these two methods are not suitable for all types of data. That is, not all data is suitable for smoothing with a moving window method. For example, create a sinusoidal signal. For example, another example I am taking, this example is other than the window example. That is, I am taking a sinusoidal signal with injected random noise. So I have taken a sinusoidal signal. I'll close all these things. Okay. So you see here, from here, this is another example from the line number 16. So t is equal to, okay, 1 to 15 with a step size of 0.2. Some time I have taken 1 to 15, and now I have taken one sinusoidal signal, that is a is equal to sine 2 pi t plus cos 2 pi 0.5 t. Now for that signal I am injecting a noise. Intentionally I am injecting a noise, a plus 0.5 into, I am taking the random numbers, random values from the length of this time, and now I'm plotting this axis. Okay, and let us see now how this will looks like. Okay, so time, now this is my sinusoidal signal. I am framing the sinusoidal signal. Now I have framed a sign. Now I have injected intentionally a noise. Now noise, I have injected a noise. Now I am plotting. This is the plotting. See, I have plotted it. Okay, you can see now. Okay, with injected noise from T0 to, no, 1 to 15. Now you can see now this is 1 to 15 time, and this is my, okay, listen, I have again, this is my noisy data, this is injected noisy data, and this is the original data. This color is the original data, and this is the noisy data. Okay, so this sinusoidal signal consisting of both sine values as well as the noise. So now we wanted to remove that noise. So what I am doing now, I am creating a window of size 3. Okay, and now we wanted to calculate the move mean on that particular signal. So I'm calculating the move mean, and again I am plotting. Now I am plotting t, that is a time, versus a is the original signal without the noise. Okay, and also same signal, that is t, again the same axis, versus a mean. Okay, so this a mean is nothing but we have calculated the noisy signal. Okay, so we will see the difference now. Okay, access. Okay, now you can see this is the original data. This is the original data, this color, this is the original data, and this is the data that is a moving median, that is window size I have taken. So now for that, okay, so for that now a mean is equal to, now I am calculating the mean. So let us see from here. Okay, so here what happened is, the moving mean achieves the general shape of the data. So there is no change. Again, you will have the same general shape of the data, whatever you have seen, but doesn't capture the valleys. So it is not capturing, it is not doing anything, okay, very accurately. Since the valley points are surrounded by two larger neighbors in each window, the mean is not a very good approximation to those points. So here, if you see this graph, okay, in this graph you can see these are the valley points. Okay, so these valley points are not at all filtered with a movement technique, because it has a larger neighborhoods. So you can see here, for this is our required signal, so side you have the noise along with that. So that is the reason movement is not an approximation method. So moving is not an approximation method. Even if you take a larger size window also, the mean eliminates the shorter peaks altogether. For this type of data, you might consider alternative smoothing techniques. So for this type of examples, for this type of signals, you cannot use the movement method. So we will see the alternating techniques. So in the alternating techniques, there are some common smoothing techniques. One is the smooth data function. This is one technique. The smooth data function provides a several smoothing options, such as the Shabaki-Gole method. This is one method, Shabaki-Gole method, which is a popular smoothing technique used in signal processing technology. So by default, smooth data chooses the best guess window size. So when you are using a smooth data, it automatically makes the best size window for the method depending on that particular data. So use the Shabaki-Gole method to smooth the noisy signal, that is a noise. That's what we have created. That is a noise with a sinusoidal information, and output the window size that it uses. This method provides a better valley approximation compared with to the move mean. So the robust lowest method is another smoothing method. So this is also another smoothing method that is particularly helpful when outliers are present in the data in addition to the noise. Inject an outlier into the noise data and use robust lowest to smooth the data, which eliminates the outlier. So this robust lowest method is used only when if a data consisting of both noise as well as outlier. If a data consisting of only noise, then the best method is Shabaki-Gole method. Okay, so both we will see now in the program. So you can see here, now I'm calculating the move mean. Okay, now I am plotting. You can see the plot. There will be no change with the move mean. See, there is not much change with the movement. You can see these are still present. These are our noise. These are still present. So okay, let me complete these things. Now what we do is, so as we as we have seen, like, this movement technique is not suitable for this type of data. So what we are doing is we are using other common smoothing methods. In that we are using Shagole method, that is a Shagole and window with smooth data function. So what this smooth data function is, it by default it takes the best window size, and for that now we are plotting the, okay, you can see now, you can see there is a difference now. You can see the difference. Just wait to understand still better. We will be adding the, okay, legend, 1 minute. So, oh, okay, original data and Shaki Gole location the best. This is the legend I have not added so that you cannot understand this. So now I have added the legend, and you can see, yeah, here it is. This is the original data and this is the Shaki Gole method. Okay, so this is the Shake Gole method. So unnecessarily that noise has been removed here. Okay, so this is the best technique, like we can use instead of that move mean. And now we can see another one, that is robust lowness. So I'll remove this. So robust lowness. So for that, just I'm adding some values here. I'll explain these values later by while showing the graph. So a row less smooth data noise, row less 5. Now I'm plotting this. Okay, you can see now this is the outlier. That means this data consisting of noise plus sinusoidal plus that 36 is nothing but we have the, this is the outlier, and the 36 plus the 20. What is the 20? Is the amplitude of the outlier. What is an outlier? Outlier is nothing but a boundary. That means a signal will have a certain boundary. Like for example, if you see here, approximately here is at some 2, I think. Yes, 2. So 1.89 or almost 2. So the complete boundary of the data is at 2, but suddenly there is 20. So that means beyond the boundary. So the beyond the boundary, whatever the signal presents, that is called an outlier. So for this type of signals, we have to use that robust lowness. Okay, right. So now you can see the graph. Yes, you can see now this is the robust lowness. This color, this color is the robust lowness. This is the normal noisy data. This is the noisy data here. Okay, so I hope you understood now these both. Now we will see the move median. Now, detecting the outliers. So, outlier in a data can significantly skew data processing results and other computed quantities. So, unnecessarily outlier will disturb the data information. So, for example, if you try to smooth the data containing outliers with a moving median, you can get misleading peaks or valleys. So misleading peaks or valleys, moving median is not a perfect method. So there is a function called isOutlier function. There is a function called isOutlier function, returns a logical one when an outlier is detected. So when there is an outlier in the data, by using this function we can find it out whether there is an outlier present in the data or not. If isOutlier is logically 1, then that indicates that there is an outlier present in the data. Verify the index and value of the outlier in a noise. So we have taken already an example, a noise. Okay, so we will go to this program. Okay, you can see now detecting the outliers here. A median is equal to smooth data, a noise of mu median, and we are plotting the data. And this is not the perfect method, because it cannot clearly identify whether there is an outlier present or not. So for that, to detect the outliers, what we are using is, we are using a function called isOutlier. If this is equal to 1, then that means there is an outlier present in that data. Okay, so I will. Okay, so a mean, now plot. See, I have plotted. So there's an outlier, we know that, but in a big data we does not know like what is, whether the outlier is present or not. Okay, just I'm keeping the present, because with move median nothing happens. That means we cannot detect it. So now I am using the function called tf is equal to isOutlier a noise. Okay, now you can see the tf value. This is the tf. Just yes, you can see now the tf 1 by 71 is outlier, that is first row and 71 columns. You can see here, is an outlier present? No. So there is no outlier present. Okay, so this is index. Now we are calculating the index, that is IND, is index value is 36. So index value is 36. So now there is no outlier. So you can replace the outliers in your data by using fill outlier function, and select the filling method. Okay, so just wait, again we will go into this program. Okay, now a outlier is equal to a noise of index. So a outlier is equal to a noise of index. So where is the a outlier here? Yeah, this is the value. That is, a outlier is the amplitude of the outlier. Now we are filling this outlier. A fill is equal to, okay, so now we will plot the axis. We will plot the graph. See, plot t comma a noise and t comma a fill. That is on a single time axis. We are plotting both a noise. Okay, because already a noise means the data with a noise. Similarly, a fill, that means we have filled the data with an outlier. So now you can see this graph. Yeah, see, this is the circle plot. I will use the legend so that you can understand. now you can see in the graph. Now you can see here, this is a noisy data with filled outlier. This is a noisy data with filled outlier, and this is the noisy data with normal outlier. Already whatever it is present, that is an outlier. This is a complete filled outlier. Okay. So alternatively, you can remove the outliers from your data by using the rm outliers function. So if you want to remove the data, you can immediately remove that data. So for that, okay, this is the, see, I wanted to remove the outlier, so I am using rm outliers function here. Okay, now after removing, I am plotting. Okay, access type and lesson. Okay, now you can see the graph. See, this is the noisy data with outlier remover. So this is the noisy data with outlier remover, and this is the noisy data with outliers. You can see now, these are the outlier removals. Okay, so like that you can calculate the you can find it out outliers, whether the outliers are present or not. Okay, now we will go for the non-uniform data. So not all data consisting of equally spaced points. So there are certain data which does not contains equally spaced points, which can affect the methods of data processing. So for example, we will create a date time vector that contains irregular sampling times of the data in air registers. So the time vector represents the samples taken every minute for first 30 minutes. So for first 30 minutes, for every minute, we have taken the time vector represented samples. Okay, then hourly over the 2 days. Then afterwards for 2 days, we will go for hourly. So for that, there is again a separate program called non-uniform data.m. So we will go to that program now. I'm closing this. Just I will clear everything. Okay, now I will go for the non-uniform data. I'll open this. Okay, this is the non-uniform data now. So now in this non-uniform data, okay, so by default smoothest with respect to equally spaced integers. Okay, but in this case, that is 1 to 78, like that. So since the integer timestamps do not coordinate with the sampling of the points in air reg, the first half hour of the data still appears noisy after smoothing. Okay, so we will go to that. Okay, you can see now I have taken t naught is equal to date time, that is 2023, that is the year 111. Some values I have taken. Now time in minutes is, okay, so I am sorting, that is t naught plus minutes I am taking 1 to 30, and now time hours is hours 1 to 48, that is 2 days. Now time is equal to time minutes, okay, and time hours. Now air register, that's air reg is equal to randomly we have taken the noise. Now the plot, okay, and a default smooth data, that is air reg move mean 3, and we are plotting this with an axis. Okay, then legend, we have, that is a legend. Now a sample points is equal to smooth data. Now we are using the move mean technique, okay, for 3 hours, and now we are plotting. So now I will run this program, entire program. You can see the, yes, you can see this now. Now you can see the first, that is a Jan 1, 6 o'clock, again 12 o'clock, that is 6 to 12, how much? 7, 8, 9, 10, 11, 12 for every 6 hours. Next 18, that is evening 6 o'clock. Next Jan 2nd, okay, 12 o'clock, again 6 o'clock, like that. If you see here, this is the original data and this is the smooth data with sample points. This is the smooth data with sample points, and this, but still there is a first 20 seconds there is a uh, like a noisy data present here. Okay, so many data processing functions in MATLAB, including smooth data, move, mean, and fill outliers, allow you to provide sample points, ensuring that the data is processed relatively to its sample units and frequencies. To remove the high frequency variations in the first half hour of data in air reg, that's what in that example air reg, we wanted to remove the first high frequency variations we have seen in the first half hour of the data. Use the sample points name value argument with the timestamps in time. Okay, so that's what already I have shown you. Okay, here you can see first half an hour. This is the what default smooth data. Okay, so first half an hour we are using the movement technique and we are sampling. Okay, so okay, so conclusion is, in this lecture you have learned about the MATLAB fundamentals, formation of complex matrices, and various types of arrays. You also have learned the most important parts of smart condition monitoring system technologies, data preprocessing by using various data analysis techniques with real-time examples. So thank you so much for watching this presentation. This is a very important presentation, and please practice whatever the examples will be given along with this data. Those are the real-time examples and real raw files. And this complete lecture has been divided into two parts in the last class. That is for part 1 lecture, and this is the part 2 lecture. If you can understand the concepts in this lecture, then the next lectures will be very easily you can follow, and you can even understand very easily the next lectures. And also the important thing is practice whatever the programs with raw files have been given along with this data in the MATLAB, because MATLAB is a powerful software. Not only these lectures helps to this technology but also various other applications. So thank you so much.